Problem 1377, 1377, 137.7, 377. Frog position after T seconds. This problem was a suggestion from one of my subscribers. I really appreciate you suggesting this problem. I hope my solution makes sense. This is definitely one of those strange kind of situation, circumstantial problems where there's all these edge cases you have to think about, and you have to make sure you read the problem description very clearly and concisely with emphasis and focus, because, well, otherwise you'll miss some of the points which are going to affect the way that this problem is solved. It's a strange problem, so let's go ahead and get right into it, and let's read the description slowly so we have a full, all-encompassing understanding of how we're supposed to solve this. Okay, so you're given an undirected tree consisting of n vertices numbered from 1 to n. Okay, that's normal, right? We're used to something similar to that when we're doing tree problems. Knowing that it's a tree, right? There's no cycles, so that'll help us perhaps when we think about how we traverse and what we have to keep account for. A frog starts jumping from vertex 1. In 1 second, the frog jumps from its current vertex to another unvisited vertex if they are directly connected, okay? So a frog's in one vertex, unvisited. So if a frog is in this position and it has neighbors, right? If the frog is here, assume that the frog came this direction, right? It'll jump to one of these 3 vertexes. Now, since its parent is here, it won't consider this vertex. It'll just jump to one of these 3. It won't jump back to a visitor vertex, okay? In case the frog can jump to several vertices, it'll jump randomly to one of them with the same probability, right? So since this frog came this direction, it won't travel here. With equal probability, it'll travel to one of these 3 bottom vertices. So with 1/3 chance, it'll go down this way. With 1/3 chance, it'll go down this way. And with 1/3 chance, it'll go down this way, right? So there's a 33% chance that I jump to this left one, to the center one, to this right one from this state that I'm at currently. Otherwise, when the frog cannot jump to any unvisited vertex, it jumps forever in the same vertex. Okay, so if we imagine that this was the whole tree from this state, right? If the frog went down this link and the frog was now here, right? Well, it's already traversed this node. So if it's here, it can only stay here. So with 100% probability, right? With 1 out of 1 probability, it's going to stay in this state. Okay, so that's something we have to think about, I guess, right? Because usually, like, you're somewhere, you're not somewhere. What does that mean? The edges of the undirected tree are given in array edges, where edges I equal to I. Okay, so it's not given in the graph format that we usually like, right? Where it's an adjacency list. So for any node, we know the neighboring nodes. It's given as just the edges that exist within the graph. So we're going to have to do some pre-computation to kind of get this in a form where it's easier to manage. Okay. Return the probability, yikes, that after t seconds, the frog is on the vertex target. Answer within 10 to the negative 5 of the... Okay, so there's a small discrepancy. We don't have to worry about that. Okay. So in this example, we have a frog. Remember, the frog always starts at position 1. There's a... So let's actually write it out. I didn't want to, but I guess it's probably a good idea. Okay, so 1, 3, 2, 1. Okay, 1, 3, 2, 1. Okay, so this frog starts at position 1, and it wants to get to position 4, right? So I guess the first thing you have to realize when you do this problem, something you have to calculate, you have to understand, is how probabilities will work in this system, right? What's the probability you get to any node? Well, I guess when you look at this problem first, right, if the frog, I'm going to try to draw a frog, because why not? If the frog is, I'm going to do this all based on what I'm looking at. That's way too big. And then the legs. Then the beady little eyes. So that's my frog. That's not bad, right? I'm not excited about it, but can you not make it bigger? I guess you can't do that in notes. So if my frog is here, right? with equal probability, it'll go to any child node, right? So there's a 1/3 probability. Let's do red. There's a 1/3 probability it goes down this link, right? There's a 1/3 probability, 1/3, 1/3, 1/3. Okay. So 1/3 of the time it'll go down here. 1/3 of the time it'll go down here. 1/3 of the time it'll go down here. When you get to 7, right? If we could, so then if we look at each other state, right? We could say, well, yikes. I'm gonna erase the frog and just do a green. It was a fun exercise, but it's getting a little frustrating. So let's just do an X. That's the frog. This green X. Or let's do a green F. So that's our green frog. So if our F is here, right? 1/3 of the time it'll go down here. 1/3 of the time it'll go down here. 1/3 of the time it'll go down here. If it ends up in this state at 7, 100% of the time it's going to stay at 7, right? Because it's like stuck. Because it's already traversed 1, so it won't traverse 1 again. And now it's stuck here and it has nowhere else to go. So 100% of the time it'll stay here. Okay. How about here? Well, 100% of the time it has no choice but to go down here. And 100% of the time it'll stay here, right? So 1/3 of the time you'll be here. And 100% of the time that you're here, you'll end up here, right? So this happens 1 out of 1 times, right? Because there's 1 out of 1 times that you end up here. You go down this link, and 1 out of 1 times. So 1/3 of the time, 100% of the time, you go down this link. So this state happens 1/3 times 1 over 1 times 1 over 1 times. I mean, it's just 1 over 1, so it doesn't matter. But that's this, right? This, you end up in this state 1/3 of the time. You end up in this state 1/3 of the time. You end up in this state 1/3 of the time. So 1/3 of the time you're here, okay? So you're kind of like imagining this pie, which is a whole unit size of 1. It's everywhere you could be is 100% probability. 100% probability you're going to be somewhere, right? 1/3 of that time, so you cut that pie into thirds, you'll be here, okay? So 1/3 of the time now you're in this system, okay? And then you have 2 options. So 1/2 of that 1/3 of the time you'll be in this state, and 1/2 of that 1/3 time you'll be in this state, right? But that really means 1/3 of the time, it takes 1/3 of the time to get here, and 1/2 of that 1/3 time you'll be here. So this is 1/3 times 1/2 time, you'll be at 4, and 1/3 times 1/2 time, you'll be at 6, right? And then for the remaining of the time, if t was like 12, you would stay in this position, right? You'd be stuck in a sunk position. So basically, at every state, the number of ways from the previous state you could get there, that's the probability that you could be in that state, times the probability that you would get to the parent state, right? The probability that I would get to 4, right? The probability of 4 equals the probability that I'd go from the parent to 4, right? The probability that I go from the parent and use this length times the probability that I'd get to the parent, right? That's always true, right? Because what's the probability that I get to the parent to 4? Well, the probability that I go from the parent to 4 is just the number of options, 1 divided by the number of options that this parent had, right? This parent had 2 options. So that means that the probability that the parent would choose me is 1 out of 2, right? And the probability that I get to the parent is 1/3. Equals 1/6, and that's the answer, right? 1/6, 1 divided by 6, 0.011666. So to solve this problem, we need to consider these facts that, well, first, you know, if you get stuck at a sink, right? What's the probability if we looked at a system like this, right? So imagine we just had one node like this, a 7. What's the probability of 7, that you'll end up at 7? It's 100%, right? So if you're at a node like this, right? If you're at I guess the idea I'm trying to say here is, if you have no children, the probability that that happens is 100% because you have nowhere to go, right? Likewise, if you have just one child, the probability that you go to that child is 100%, right? Like when we looked at this system here, right? Like this event here, you were stuck with a probability of 100%, which is why it's only 1/3, right? This chain here is also 100%, right? It always is going to end up that way. There's no choices. There's no options. If I have no children, there's no options. So the probability that I'm in this state is 100%. And if I only have one child, again, I have no options. I have to choose that child. If I have less than or equal to one child, so either I'm a leaf node myself, or I only have one child, the probability is 100% going down that link, right? Because there's no other choices. I'm forced to go down this link, okay? Now, we don't want to have a situation where this green frog starts here and goes here and goes here and then goes back up and goes down and goes back up, right? Because you can't traverse the same state twice. So since this is a tree, there's no cycles. So I only need to keep account of where I came from. So who my parent is and not traverse my parent, right? When I'm at 2 and I came from 1, I don't need to think about every node that I've traversed in the system. I just need to keep information about 1 that I've already traversed 1. That way I don't traverse it again. Then when I go to 4, I keep information about 2 and I don't traverse to 2 because I say, okay, I've looked at 2 already. 2 is my parent. So that's the general idea behind what you need to keep account for. You just need to keep account of the parent that you've looked at. And then in each state, you need to keep track of the probability of the parent, right? The probability coming into me times the probability that the parent would choose me, right? That information is also important. And then I guess something else we have to consider is that we want to find out if the frog is in a state at time equals 0. So one little thing that might fool you, right, that you could, the common mistake that you can make that I've made, right, is say we had a tree like this and our target is 2. Our target right here, right? So imagine this is our target and our time equals 2. So you might feel inclined, right, to say, okay, I start here, and then after a second, I end up here. I'm done, right? But remember, for this thing to work, you have to be at the target at time equals 0, right? So even though you're already at the target, you have to keep jumping. So you jump down, and then after 2 seconds, you're going to be here. Right, so since you're here at 2 seconds, you can never actually reach the target, right? There's no way to reach the target in 2 seconds because you have to go down in 1 second and you have to go down again in 2 seconds. So just because you reach the target doesn't mean you found a solution. You have to reach the target when there's no time left, right? So either you reach the target when there's no time left, or the target is a sync node, meaning that the target is a leaf, right? Because if the target is a leaf, after 1 second, you'll be at the target. And then after another second, you'll still be at the target. So we could, run through additional transactions, but we know for a fact, if we're at a leaf node for the rest of time that's remaining, we'll still be at the leaf node. So if we reach a leaf node, we don't need to keep traversing over and over again to figure out okay, what happens at the next time? What happens at the next time? We know what's going to happen for the rest of the time remaining if we're at a leaf node because there's nowhere else we can go. We're going to be stuck at this leaf node. Okay. So that's something else you need to consider. So with all those observations, right, which I just went through crazily and I probably should have wrote them down. Let's try to solve this problem. Okay. So first thing we want to do is we want to convert the edges into a graph that we're more comfortable utilizing to efficiently solve this problem. So we'll create a graph. And then what I'm going to do, since this starts at 1, but you 0 index a graph, we're just going to create we'll create one additional indice, so then the 0 indice will always be empty. This is just an easy way to create this graph. Then we'll look at each edge in the graph, and we'll add them so that we can create this tree. But notice this tree is not going to be, it's going to be bidirectional, so we're going to have to keep information about the parent so that we don't traverse things that we've already traversed. Okay. And then we're going to run DFS to solve this problem, right? So you have the current node you're looking at, the parent, we'll call that P, and the probability that this state occurs. So we'll call the parent none. So the first time the parent will be none. The probability that something occurs will start at 1, right? And it'll continue to get smaller, right? The probability of that you're at 1 in the beginning is 1. And then, okay, we also need to keep track of time. All right, so what time are we at within the system? How much time has occurred? Okay. So how do we know if we're done? So if time equals 0, we're done, right? So we'll start there, right? Because we're going to keep traversing until time equals 0. And then when time equals 0, we're going to assess like, okay, where are we? Are we in a position? Are we in a position where we're at the target? So we'll return the probability that we got in this position times int u equals target. So what this is basically saying is if we're at the target, then we'll consider this probability, right? Because if we're not at the target, then we don't care about the probability to get to the target because we're just trying to find the probability to get to the target, right? So we're trying to find the probability to get to the target. So if we found a probability to get somewhere that isn't the target, we don't care about it. So we'll just say 0, right? The probability that this state gets us to the target is 0 because this isn't the target, right? Because we've run out of time. So we're at the end of time. We've jumped around as much as we can every second. We get to t equals 0. We're at the end state. If we're at the target, then we return that probability because that'll be the probability to get to the target. If time equals 0 and we're not at the target, then we're not at the target. So we don't care about what this probability value is because this probability won't get us to the target because we're not at the target and we run out of time. So we return 0. Okay, so this will return the probability if we're at the target. Now, in other cases, what if t is greater than 0, but we're in a state like this? Okay, what if we're at the target, but time equals 2? Right? Well, we're still going to end up being at the target when time equals 0. So if time equals 0, or we're in a state where we have no children. So what does it mean to not have any children? So if time equals 0, or we have no children, what would that mean? Okay, so to have no children would mean that the length of our graph is 0. Right? Because there's nowhere for us to go. So in this case, right, the length of the graph at this node is actually 1, right? Because the number of children, sorry, not the length. The length of the graph of u is the number of children of u, right? So the number of children of this thing is 1. But it's not actually 1 because this parent has already been traversed, so you can't traverse to it again, right? So when you get to this node, if you start at 1 and you go down and you get to this node, the number of children you can explore is 0, right? So the number of children you can explore is, well, the length of the number of children that you have minus the number of children that you have, that you minus the parent, right? So if this is not equal none, that means that you've traversed a parent already, right? The only time this will be none is when the first parent runs. So when you're here, right, when you're here at this node, the length of the graph is 1, right? The number of children you have is 1 because technically you could go to 2, but you subtract 1 for the fact that your parent exists, so you can't traverse your parent, right? Because p not equals none mean that my parent exists, so I can't traverse my parent, so effectively I have 0 children. So if that's less than 1, so I'm just thinking about how this works because it's a little confusing. I don't even think I need parentheses here. So if that's the fact, so if you're stuck at a state, like if you're stuck at a state 7, right? So here you start, you have 2 seconds. So at 1 second, you're at 7. So you're saying, okay, I have 0 children. So I can just return 0 here. I don't need to keep going over the system over and over and over again. I only need to look at this state once to make a decision. And we'll put that on one line because we're fancy. And then otherwise what we're going to do is we'll return the max probability, right? Because if we don't get to the state, we'll just return 0. So in order to get to the state, we'd have to return something greater than 0. So the maximum value we get would be the probability to get to the state. Because if we get to the final target state at time equals 0, we'll return a non-zero probability. Otherwise, we'll always return 0. So we'll just get a bunch of zeros returned, and then one of the values we get returned, if we can reach the target, will be non-zero. So then this max will capture that non-zero value. So we'll run DFS on each of the children of the current node with 1 second less, because we just used the second to traverse to that node. The parent will now be us, right? If we're at state 1 and we want to look at the child 2, we have 1 less seconds, right? 1 less second, and the parent will be 1. Because we go from 1 to 2, now we're looking at 2 with the parent equaling to 1. So we go to 2 from 1, now the parent is 1. Okay, and then now what's the probability that we go to this state? The probability that we go to the next state is our own probability, prob, times 1 divided by, what's the probability that I choose this state? Well, that would be the length of the graph, so the number of children that I have, minus 1, right? Because minus my parent. Minus my parent? Wait. Only if, so this would have 3, because it has 3 children, but since it's the root. So if P not equal none, right? So the number of effective children that I have, right? Because for this thing, P would be none, so it would have 3 effective children. Versus this thing, it would have 3 children, but only 2 effective children. So you subtract out the 1 child. So that would be the probability that I get to a child, right, is my probability times the probability that I choose that child. Okay. And then I do that for each child in G of U if V not equal P, because I don't want to consider the parent. Okay. And then it could be the case that I have, no. I'll always have 1 parent. I'll always have 1 child to traverse because of this condition here. So I don't need to do that. Okay, and then we'll just return DFS. We'll start, the frog starts at node 1 with time t, and then these things will be defaulted to none. I have no parent, and the probability that I start at node 1 is 100%. Not enough values. Okay, why did I do that? So we're looking at each edge and edges. All right, let's submit that. And let's pray. Definitely could be a mistake here. All right, cool. There we go. So that's a pretty short solution, all things considered. So what's the runtime of this? And what's the space? That's pretty hard, actually, because it's a weird problem. Okay, so let's do time and space. Let's think about it. So we have to add each edge. So let's say that, so n is the number of vertices. It's already given. M equals target, or no, m equals length of edges. So we have to add each edge. So that's going to take m time. And then we create a graph that's the size of the number of vertices. But you could have like 20 vertices and no edges in between them. So that's going to take m plus n time to do that. And then for DFS, even if time is greater than... So you're going to traverse this entire graph starting from 1. You'll traverse the entire graph. And if you get to an edge before, so if like time was 1,000,000, but you only had 4 vertices, by the time you explore the whole graph, you'll have nowhere else to go and time will be still large. So even if time is large, you'll end up only traversing the entire graph once, right? I'm only going to traverse the entire graph 1 time. I'm going to look at each vertice 1 time. Now, since this is a tree, there are this is a tree, so the length of edges at most could be m minus 1. So we don't even need this factor here, right? Because the number of edges is always less than the number of vertices. So we don't actually need to keep track of that, right? Because it's always going to be less than n. So it's always going to be less than 2n. So n is fine here. And we're only going to look at each vertice once, right? Because if we get to the end of the graph, if we've explored everything and there's still time remaining, we'll know the probability of that state. So we'll only look at each state once. So this will only run for each n vertices at most. And then for each one, you do a constant calculation. You know, you look at each of your children, right? But for each of your children, you're only going to look at all those children once. And you'll never have a situation where you look at the same thing twice. So that's also n time. So this will take n time. This will take n time. This will take less than n time. So it's 3n time, big O of n. Now for space, we'll have each, we'll have to create a graph. We create this graph, right? And there's n vertices, so we'll have n space. We'll have to add each edge, but since it's a tree, there's less edges than there are vertices. So that'll be less than n, so it's 2n, so still n. And then for this, we'll have to create a recursive stack going downwards for each node that we traverse. But we'll only traverse at most n nodes, so that'll create n stack space. So that's O of 3n again, but that's just big O of n. So this is a big O of n time complexity, big O of n space complexity. There you go. See you.